This video I'm going to prove an interesting theorem. For each positive integer n greater than or equal to 1, the sum of mu of d, where we sum over all the divisors of n, is equal to 1 if n is 1, and it equals to 0 otherwise if n is bigger than 1. Before we get into the proof, I have two comments to make. One is that it would be great if you subscribe to my channel, especially if you're into viewing mathematical proofs. That's all we do on this channel. The other thing is I like to define what mu of n is. Mu of n, by definition, either it equals 1, 0, or negative 1 to an positive integer. It equals 1 if n is 1. That is, mu of 1 is 1. And it equals 0 if the square of some prime divides n. If p squared divides n for some prime p. And it equals negative 1 to the r if n is a product of r primes, all to the first power. Because the instant you have a power 2 or bigger, then p squared goes into p1 cubed, p squared up to pr. Because this is a multiple of that. Or, you can see it. P squared really, P1 square, really divides into this. I can tell you exactly how many times. P1 squared goes into P1 cubed P1 times. So, it did go in. Went in that many times. The power is 2, then it would go in 1 time. That is, if this were P1 squared, then that prime squared goes into this many times. P2 times P3 up to PR. Whenever that happens, mu of n is 0. Okay, so now that we have the definition of mu of n, maybe I can try to move it over to the side over here. Not really, but okay. So, let us consider the proof. Okay. The summation, so let's just say first, let n equal 1. So the summation of mu of d as d divides 1. So the only positive number that divides 1 is 1. So this is just mu of 1. And by definition, mu of 1 equals to 1. Okay, that's what they said it would be. Now, what if n is bigger than 1? Let n be bigger than 1. Okay. Let n be bigger than 1. Then n is equal to p1 to the k1 times p2 to the k2, all the way down to pr to their kr. since mu is a multiplicative function, it suffices to show the result holds for n is equal to just p to the k. Okay, so we have the summation as d divides n, which is p to the k, of mu of d. Okay, well, the divisors of p to the k are 1 and p squared all the way up to p to the k. So it's mu of 1 plus mu of p plus mu of p squared all the way up to mu of p to the k. Well, by definition, mu of 1 is 1, and this is only 1 prime, so it's going to be negative 1 to the 1. And believe it or not, the rest are 0, because p squared goes into that number. Mu of p cubed. P squared goes into that number. P squared divides p to the k. So we only end up with 1 plus negative 1 to the 1, which is 1 plus negative 1. Look at that. We get back 0. Okay, we just proved, well, there were two pieces. First, let n equal 1, and then let n equal to bigger than 1, combining both cases, we proved the theorem. If you like seeing mathematical proofs like this, consider subscribing to my channel. Please click the like button. Leave a comment. I just love reading your comments. Also, see you guys in the next video. Never forget, watch and learn.